Okay, few minutes. Okay. Okay. Can you see my slide?
Yes, Ajahn.
Okay. We can continue from the previous lecture. Okay. In the previous lecture, I teach you about the circuit that contain the resistor and the inductor. Only the simple case, okay? The first case is the simple case, it means short free. Short free is mean the circuit used to drive by the short for a long time. For time equal to 0, you plug out, okay? You remove the short. The current and the voltage will be gradually drop, okay? If the circuit contain only the resistor, the current and the voltage will be suddenly drop, okay, to 0 immediately. But if the circuit contain inductor and the capacitor, the current and the voltage will be gradually drop, because in the inductor and in the capacitor, it have some energies. It perform, the capacitor and the inductor perform like the battery for a short time, okay? It try to maintain the current IL, or it try to maintain the voltage VC, okay? Okay, now in this part, we will discuss another 4 left topics. Okay, the first one is, okay, before we go to the turn on switch case, or we call them the driving sort. Okay, we will study about some mathematical symbol first. Okay, the unit step function. We have been studied the response of the RL circuit and the RC circuit when the no source or the force function will be present. Okay, already present that. Okay, when you remove the sort out, okay, the current and the voltage will be gradually dropped due to the natural response. It means the output or the response that depend only on the nature of the circuit, the size of the capacitor, the size of the resistor, the size of the inductor, and the structure connection. Any output or the response is obtained from the presence of the initial energy storage within the inductive or the capacitive element in the circuit. We have been solving the problem or example in which the energy source are removed from the circuit. Okay, all previous case, you can see that when time equal to 0, you turn out the source, or you maybe remove the source by some switching circuit. Okay, it's due to in the source it have only resistor and capacitor, or the resistor and the inductor. Okay, the current and the voltage will be dropped to 0. Okay, but in this section, we consider in another point of view. We must consider that type of the response with the result when the energy source are suddenly applied to the circuit instead. Okay, the certain special force functions which are discontinuous or has discontinuous derivatives are called the singularity function, or sometimes we call them the unit step and the unit impulse. Okay, the unit step and the unit impulse we will study in the signal and system subject. But in this class, in the circuit, we concentrate only on the unit step function. The unit step function is mean for time less than 0 or time less than t0, it equal to 0. Time greater than t0, it equal to 1. You can see that, okay, the unit step of, we use them ut. Ut is perform like the switch on circuit saw. Okay, when time less than 0, the circuit is still turned off. Okay, when time greater than 0, it's turned on. Okay, in the mathematics formulation, you can see that it states that time less than 0, it equal to here. Time less than 0, it equal to 1. But it never states what about the time equal to 0. Therefore, the riser don't exist in the definition directly. Although the risers is not strictly a part of the definition of the unit step, it is usually shown in each drawing. In the circuit analysis, a discontinuity or a switching action often takes place at an instant that is defined at time equal to 0. Okay. In general, if the switch is activated at time equal to 0, we substitute T0 equal to 0. Okay, it means for time less than 0, it equal to 0. Time greater than 0, it equal to 1. Okay. Now we will consider about the UT or the unit step here first. Okay. In the physical sort, okay, or the and how to use or how to implement the unit step, okay, compare for the switch point of view. Okay, in this case, we use UT minus 0.2. It means the switch is activated at time equal to 0.2 second. Okay, it means for time less than 0.2. The time less than 0.2, okay, the switch is don't activate yet. It means, okay, it lies, okay, the switch is open in this case. If the switch is open, it means the source is no longer supply the energies to the general networks. Okay, therefore, the current and the voltage will be 0. Okay, before time equal to 0.2 second. For time less than 0.2 second, you can see that, okay, the switch is not open yet, okay, and the source is seem to be deactivated. How to kill the voltage source? You can kill the voltage source by short circuit them, or here in the switch point of view, it seems you broken them. Okay, in the switch you don't activate anything to them. Okay. Okay, the source is 0. Okay, when time greater than 0, the switch in UT is equal to 1. Okay, if UT equal to 1, you can see that UT equal to 1. Okay, you multiply 1 with 5, give you 5 volt. Okay, give you 5 volt. Or when time is equal to, time equal to or greater than 2. If time is greater than 2, the switch is placed in this position, and this means the source is connected to the general network. It means the source is now have the ability to drive this network. Okay, therefore it supply 5 volt to this network by this structure. Okay, in this book, it will be show you or this script about the driver source in the two graphical case. The first one, we maybe use UT's unit step here. Okay, another one maybe use the switch position in here. Okay, maybe use the first case or the second case. Whether the questions give it to you or provide this circuit to you, the meaning is the same. Okay, the meaning is the same. Now, after you know about the graphical point of view of the circuit diagram for the plug-in source, okay, or driven source, okay, some very useful force functions may be obtained by manipulating a unit step, okay, such as let us define the rectangle voltage power by the following definite condition. You can see the complex, okay, some complex functions such as the rectangle. You can see that 0 for time less than T0 and 0 for time greater than T1, okay, but between them it gives you V, okay, the rectangle waveform. This rectangle waveform, you can represent them, write them in the term of the unit step, two unit step function, subtract each other, okay. The first one, okay, the first unit step have the time delay at T0, and the second one have the time delay at T1. Okay, what about this graph? You, okay, in order to get the final answers, okay, we at T minus T0 is here. It means you will get, okay, you get the pink one first, okay. The pink one is here. We UT minus T0 is here. Okay, you can see that this is only the rectangle. For time less than 0, it equal to 0. Okay, and for time greater than 0, it equal to here. Okay, both of them, the pink and the orange, is the same. Okay, now for time between T1 and T1, okay, between T0 and T1, you can see that only this source is activated. Okay, only this first source is activated. Okay, the pink source is activated, but the orange source is not activated yet. Therefore, when you adding them, the result, the output voltage equal to V0 during this period. Okay, for time greater than T1, what happened? Time greater than T1, okay, we have two voltages activated, the pink one and the orange one. Okay, both of them is activated, but the voltage that it generates is opposite each other. Therefore, it will be cancel each other effects. Okay, the sum of them is 0. Okay, this is the shape of the output result, the rectangle. You can see that the rectangle. Or it means in this example case, we will show you that. Okay, if you have the rectangle, you can write them in the unit step function, a simple unit step function. Therefore, a unit step function is a very powerful mathematics function that we can express the complex function. Okay. Now, after you know about the unit step function and some application of them, we start to concentrate on the driven RL circuit. The driven RL circuit is show you in here. The step to compute the driven RL circuit will be show you in this 4 steps. I will be summary from the textbook. Okay, you remember them and try to apply them in the example step by step. Okay, the first one, determine IL first. Okay, how to determine IL? We have about 4 steps to determine IL. The first one, determine IL as time less than 0 or time before switch is activated. Okay, before the switch is activated, you determine IL and you see inductor perform like the short circuit. Okay, you can use the DC analysis method to determine the inductor current. Okay, the second one, determine the inductor current at time equal to infinity. Okay, the inductor is still perform like the short circuit again, but in this case, we consider the circuit after the switch is activated. You can use the DC analysis method to determine the inductor current. Okay, next one, you determine IL for time greater than 0. Okay, for time greater than 0 without independent source, 0 out. Okay, in this step, okay, you can kill every source. Okay, how to kill the current source? You can kill the current source by the current source you kill by open circuit them. For the voltage source, you can kill them by short circuit them. And after that, you determine the equivalent resistor and equivalent inductor. Okay. After that, you get tau. Okay, the ratio between the inductor and the resistor. Okay, the total response IL for time greater than 0 equal to IL at time infinity that you determine from the second step. Plot with I naught, okay, multiply with E power minus T divided by tau. Tau you compute from the previous step. Okay, tau equal to L, the ratio of the inductor and the resistor. Okay, and the last one, okay, you can determine this value I initial condition. I had at the initial condition by set, okay, IL for time greater than 0 equal to IL for time less than 0. Okay, and you can get I hat at that point. After that, if you would like to determine the other parameters such as VL or IL or IR or the other, you derive them from IL only. IL only. Only IL or only the inductor current you can trust. Okay, you can believe it. The others parameter you cannot. Now, in order to give you more understand, we will provide you the example. Okay. Okay, from these circuit figures, determine and the sketch the inductor current and determine and the sketch the inductor voltage. Okay. Now, from the previous step that you must determine IL for the driving case. Okay. For the IL for the driving case, checking that is driving case or not. You check at time infinity. Okay. At time infinity, any source is still in your circuit or not. In this case, at time equal to infinity, this source equal to 12 volt, and the 12 volt is already drive the circuit until the infinity time. Okay, therefore, in this case, it's the driving source. For the driving source, you must determine the RL, the driving RL circuit. You must determine IL for time less than 0 first, or before the switch is active in this case. Okay, in this case, the switch is not active at 0. Switch is active at 3 seconds. Okay. Determines IL for time less than 3 seconds. Less than 3 seconds, the source is no longer activated yet. Therefore, the voltage is 0. Okay, the voltage is 0 is mean nothing in your circuit. Okay, therefore IL is 0.2. No voltage supplied to the circuit, no current produced by the source and the other part. Okay, IL equal to 0 at that time. Now, the second step, determine IL for time infinity. For time infinity, okay, the source is activated and it equal to 12 volt fixed at that point for a long time. Okay, therefore, in this case, the inductor is performed like short circuit to the DC current, okay, because it will be full charge in the inductor point of view, okay. Now we assume any transient in the circuits died out long ago, removing the period DC circuit and the inductor act like the short circuit to the DC current. If it's short circuit in here, you can determine IR very easy. From the Ohm's law, V equal to IR. I equal to V divided by R equal to 12 divided by 1K. Therefore, the current at time equal to infinity equal to 12 milliamp. Equal to 12 milliamp. Now we determine, okay, in the 1.3 step, okay, the third step for IL. The third step for IL, you determine L equivalent and R equivalent, okay, the equivalent inductor and the equivalent resistor, okay. In this case, the circuit have only a single resistor and a single inductor. Therefore, that single resistor equal to 1K and the single inductor equal to 50 millihenry. Okay, substitute them, you get the time constant equal to 50 micro. Therefore, the general solution of the RL will be in this form. IL infinity, you get them equal to 12 milliamp. Okay, 12 milliamp is here, IL infinity. And the time constant, okay, equal to 50 micro. Okay, and the switch is activated at time equal to 3 seconds. 3 seconds, use the shifting time every t by 3 seconds. Yeah. Now it's a, okay, 1.3. But in this case, you can see that the inductor current that you determine is not clearly perfect. Okay, because it still have some unknown. I promise here that you can determine I, the unknown, by using the initial value. Okay, from the third characteristic of the inductor. It is impossible to change the current through an inductor IL by a finite amount in zero time. Therefore, 1.1 IL at time less than 3 seconds equal to the 0 because no source activated at that time yet. Okay, and equal to IL for time greater than 3 seconds is here that you compute from the previous step. Two of them is equal when time equal to 3. Okay, when time equal to 3. You substitute them, okay, left hand equal to 0, right hand is here, okay, this term will be 0, okay, anything power 0 give you 1, okay. Therefore, you get I here, the initial conditions, I equal to 12 milliamp, okay, 12 milliamp, okay, and you substitute them in the inductor current formulation, you get the complete solution in this form, okay, in this form. Checking first, okay, is the dry vent or the salt free. If it's dry vent, you use this 4 step to compute them. If it's the salt free, it's more easier, okay. Now, IL for time greater than 0 equal to 12 minus 12 e power minus 20k t minus t, okay. If the questions ask you for the other parameters such as VL, you derive them from IL. Okay, we have for the time less than 0 is very easy because it have no source, no voltage. Okay, therefore IL equal to 0, VL equal to 0 too during the time. Okay, but VL for the time greater than 0, you must compute them from ILs. Okay, take derivative of IL, L di dt. Okay, L, the inductor current that you compute from the previous step equal to 12 minus 12 e power minus 20k multiply with t minus t. Okay, take derivative up here, give you here. Okay, take derivative of constant, give you 0. Take derivative of e at, give you a e at, a e at. Okay, 20k put in here. And you can formulate, okay, simplify the equation by multiply all terms together. It gives you VL equal to 12 e power minus 20k t minus t u t minus t. Okay. In the overall point of view, we can summarize the procedure following here. IL for time less than 0 is equal to 0 because during from the circuit structure For time less than 0, it have no sort activate on your circuit, okay? But at time equal to infinity, the sort will be activated equal to 12 volt for a long time, and it will be reached to 12 milliamp soon, okay? IL for time greater than 3, okay? You can compute from the formulation that it already have, substitute, okay? Substitute the inductor and the resistor, okay? You get here, okay? IL for time less than 0, less than 3, and greater than 3 will be matching at this point, and you can use them as to determine the initial conditions, okay? You get here. Next one, you determine VL from IL. VL you can determine them from IL. VL equal to L di dt. IL is constant. V is 0. Okay. And VL for time greater than 3 seconds. Okay. We will provide you in here. Differentiate IL at the time. Give you VL at the time too. Okay. Next one, okay, in order to give you more understand, we will provide you some example case, okay. Determines, okay, RL circuit in this case. For the circuit of the following figure, determine the state, the inductor current, and the inductor voltage, okay. Especially determine the inductor current and the voltage at time equal to 3 seconds, okay, 3 seconds. In this case, the switch is activated at time equal to 0 seconds, 0 seconds. You can see that for this case, the example of this case is mean for time less than 0, it has some sort in your circuit, not 0, okay? You can see that the sort is equal to 60 volt, okay, for time less than 0. And for time greater than 0, the sort is same small size, okay? It will be equal to 20 volt instead. Okay? Determine IL for time, okay? You have 4 steps to compute. For the RL circuit, you must determine IL. IL that you determine, it have 4 steps. IL for time less than 0, IL for time infinity, IL for time greater than 0, and determines I hat, okay? By apply all 3 previous cases, okay? Any transition in the circuit died out long ago. Therefore, the inductor perform like short circuit. If it perform like short circuit, IL equal to V divided by R equal to 6 amp, okay? The second step determine IL for time infinity. For time infinity, UT equal to 1, right? If UT equal to 1, the voltage source will be reduced the size to be 20 volt instead, okay? And the inductor is performed like the short circuit again. We assume any transient in the circuit died out long ago, leaving a pure DC circuit, and the inductor act like the short circuit to the DC current. See, yeah? Therefore, you can determine I from the Ohm's law. I equal to V divided by R equal to 2 amp. Okay. Now, the third step, you would like to compute the real response of the RL circuit. Okay. L equivalent equal to 50 millihenry. R equivalent equal to 10 ohm. Therefore, the time constant equal to 5 milli. The general solution of the RL circuit is will be show you in here. Okay, IL infinity equal to, okay, equal to 2 amp. Okay, I had, and here give you here. You can see that this is the general form solution, but it still have some unknown parameter I had. Okay, you can determine I had from the previous 3 steps. Okay, by applying the third characteristic of the inductor that states the impossible to change the current through an inductor IL by a finite amount in 0 time. Okay, for time less than 0, it equal to 6 amp. For time greater than 0, it equal to 2 minus I had e power minus 200t. Okay, you can simplify them. Okay, anything. Okay, and both of them will be equal when time equal to 0. Okay, e power 0 give you 1. Therefore, you can conclude that I had equal to, okay, I had equal to, okay, minus 6, okay, minus 6. Oh, minus 4, sorry, minus 4. And when you substitute them back, it gives you plus 4 in here. Okay, IL equal to 2 plus 4 e power minus 200t ut. Okay, And next one, the questions ask you to determine IL for time equal to 3 seconds. Substitute 3 seconds in the equation. Okay, 3 milliseconds in this equation, and you will get here IL at time equal to 3 milliseconds equal to 4.3 amp. Okay, next one determines VL or from the IL. Okay, determines VL from the IL. You can determine them from the definition directly. L equal to di by dt. Okay, di by dt. In this case, IL is constant, right? IL is constant. Therefore, take derivative of constant. Give you 0. Give you 0. Okay. Next one. Okay. Determines VL for time. Okay. Determine VL for times greater than 0. Okay. Greater than 0 in this case, you must use, okay, IL for time greater than 0. IL for time greater than 0 equal to 2 plus 4 e power minus 200t. Okay. Take derivative of 2 give you 0. Take derivative of 4 EAT give you A EAT. Okay. A EAT. And after you get VL in the general form, the questions ask you to determine VL at time equal to 3 milliseconds. Okay. VL at time equal to 3 milliseconds in this case, it equal to 22 volt. Now, in the overall point of view, okay, the summaries of this procedure. For IL for time greater than 0, the switch is activated, okay? The sort is still full operate at about that, okay? Therefore, IL equal to 6 amp. For time infinity, IL will be dropped to 2 amp soon. You know that, okay? But, okay, during that time, the inductor current will be dropped. It doesn't drop suddenly. It dropped gradually in the exponential form, okay? And the value of the first, okay, IL for time greater than 0 equal to 6 amp, okay? And time greater than 0 is equal to 2 minus I times E minus 2200t, okay? Is equal. When you substitute time equal to 0 in here, okay, you can get I naught in here, or I hat in here. I hat equal to 4, okay? This is the complete general form, solution form of the IL. If you would like to find the other parameters such as VL, okay, VL for time greater than 0 is equal to 0. Due to IL is constant, take derivative of constant give you 0 too. Okay. And next one, VL for time greater than 0 is equal to 40 minus 40 e power minus 200t. After you plot every graph completely, I recommend you to observe them again. In this case, IL is possible because it cannot suddenly change, okay? It can only gradually change. And we take advantage from this step, okay, for time greater than 0 and time greater than 0, it equal, okay? And for time greater than 0 is here, the current, the one that will be differentiate the current and give you here. You can see that VL can change suddenly from 0 to minus 40 volt. Oh, yes. Okay, and drop to 0 too. Okay. Okay. Can I drink? Is 2 minutes? Okay. Sorry for that. Okay. Okay. Hello? Can we continue from the previous?
Yes, John.
Okay. Okay. We already finished. Okay. The inductors. Okay. The unit step function and the driven RL. Okay. Now we will go to the seventh. Okay. The topic 7. The natural response and the forced response. Okay. Okay. If I speak too fast, you can tell me, okay, to slow it down. Okay.
Yes, sir.
Okay. The natural response and the forced response. Okay. The complete response is composed of the two parts. Okay. The natural response and the forced response. Okay. But in the previous case, I already, okay, in the previous solution, you can see that. Okay. Yes. Okay. You can see that. Do you can see in the slide? Hello?
Yes, yes.
Okay, you can see the slide. You can see that we have two terms, right? AL, you have two terms, 2 and, yeah, 2 and plus 4, E minus 2, okay, in here. Okay, the first term is here. You can see them to be the forced response. The second term that have the exponential form, you can see them to be the, the first term is constant. We call them the forced response. Yes. The second, we call them the natural response. Okay. Now we will see you, okay, in another point of view. Okay. In the previous, you already know how to compute the complete solution by the step that I give it to you. Okay. Therefore, in the overall point of view, what happened? The complete response is composed of the two parts. The natural response in that we use in the engineering's definition. The response that depend upon the general nature of the circuit. This depend on the type of the circuit, the size of the circuit, and the interconnection of the element. The complementary solution or is we provide is sometimes we call them, okay, we can generate or compute the natural response by using the complementary solution, okay, defined from the mathematics point of view, the linear differential equations point of view, okay. The forced response from the engineering definition, okay, the response that depend only on independent source, okay. Therefore, the value of them is constant, okay, constant. Therefore, in the mathematics point of view, this part we call them a particular solution, okay, that derived from the linear differential equation. Let us consider the general equation of the ties meet in the previous section. Okay, you can see that the current, if the circuit is, okay, the RL circuit, okay, you know that, okay, IL is the form of the two terms. One is the natural response, another one is the forced response. Okay, the natural response will be in the term of the exponential decaying. Okay, and the forced response is only constant value. Okay, now we will show you again about how to compute, okay, the general form solution again. Okay, now determine and the sketch the inductor current and determine and the sketch the inductor voltage. Now it's you more determine and the sketch the current in the resistor 6 ohm. Okay, 6 ohm resistor current. Now you can see that in this case the circuit is have some unit step function. Okay, checking first. Driver sort or sort free. You check at the sort. Check at the sort. For the time at the time infinity, how many sort is activated in your circuit? In this case, this sort is activated at all time, and this sort is activated too. Therefore, both sort is activated. Okay, is mean the current the circuit is the driver source situation. Okay, if the driver source situation, you must compute IL follow my statistics, okay? IL for time less than 0. For time less than 0, this circuit is not activated yet, right? UT is not activated, okay? For time less than 0, the sort is gone, okay? It have no this sort. It have only one sort left in your circuit, and if it have only one sort in your circuit, what happened? The inductor perform like full charge. Okay, if it perform like full charge, it means the inductor perform like short circuit. Okay, we assume any transient in the circuits diode long ago, removing the pure DC circuit, and the inductor act like the short circuit to the DC current. You can see that it perform right short circuit in here. Okay, therefore in this case you can see that all this inductor is already short circuit 6 ohm, right? It means no current flow in the 6 ohm during the time. Okay, during the time. Therefore, IL equal to V divided by R equal to 25 amp. Okay, and for time infinity. At time infinity is okay. How many sort activate in this case? Both sort, right? At time infinity, this sort is activated too. 50 and 50. Okay, is series together. Okay, and the inductor is the same as the previous situation. It performs like short circuit again. We assume any transient in the circuit diode long ago, removing a purely DC circuit, and the inductor act like the short circuit to the DC circuit. Okay, to the DC current, and it means the resistor 6 ohm is already bypassed. IL equal to V divided by R. In this case, you see that, okay? For time greater than 0, okay, the sort should be double size than the previous one. Instead of 50, it will be 100, okay? Therefore, the current that flow in the IL at time infinity is double than the previous two, equal to 50 amp. Okay, next one, for time greater than 0, you can find the inductors and the resistor voltage. Now, in this case, how many resistors you have? You can see that in the circuit structure is here, right? The circuit structure is here. Okay, when you would like to determine the equivalent resistance in this case, the equivalent resistance is 2 ohm or 6 ohm or not up to, you must kill the source first. Okay, in this case, you must kill our source. Okay, we don't care it's activated or not. We don't care. Okay, we kill it. Okay, for time greater than 0, you must kill the voltage source. How to kill the voltage source? You kill by short circuit them. When you short circuit them, you can see that, okay, 2 ohm will be parallel with 6 ohm, right? 2 ohm is parallel with the 6 ohm, okay? It gives you 1.5 ohm. And the inductor is only a single inductor's value. Therefore, it equal to 3 Henry. Okay? The time constant give you here. Okay? The time constant equal to 2. Okay? Therefore, the general solution of the RL circuit will be here. Okay? Give you in this form and give you 2. Okay? Give you 2. 50 minus I house is here 2. Sorry, maybe the sequence of the slide may be a little bit earlier. Okay, yeah, okay. After you get IL for time greater than 0, okay, it equal to 50 minus I has, okay, e power minus 0.5 t ut, okay, at the 1.3. Now you can take advantage from 1.1 equal to 1.3, okay, 1.1 equal to 1.3, 1.1 for time less than 0, okay, by take advantage from the third characteristic of the inductor that states that it is impossible to change the current through an inductor IL by a finite amount in 0 time. Therefore, IL will be equal to 25 amp for time less than 0. And for time greater than 0, IL equal to 50. I had e power minus 0.5 t ut. Okay, here. And now, okay, you substitute every t to be 0. Every t to be 0. Okay, 0 multiply anything give you 0. Anything power 0 give you 1. Okay, therefore 50 equal 25 equal to 50 minus tie. I had equal to, okay, equal to 25 in this case. Substitute them inside. Okay, give you here. Okay, this is the complete solution of the IL at all time. Okay, now in this case the questions, okay, provide you here. Okay, therefore IL for the overall time equal to here unit step. For time less than 0, it equal to, okay, yeah. Now, for this case, it's ask you for time VL. If it asks you for VL, okay, VL is mean for time less than 0, it equal to 25. IL equal to 25. VL equal to L di by dt. Okay, IL is constant. Okay, therefore VL equal to 0 for time less than 0. But for time greater than 0, okay, IL is not 25 equal to 50 minus 25 E minus 0.5 T. Okay, here. Take derivative of this term. Take derivative of 50 give you 0. Take derivative of here 25 E minus AT equal to minus A 25 E minus AT is here. Okay, this term will be here. Reorganize the form, give you here. Don't forget to multiply by the inductor inductance value. Okay, the inductance value equal to 3 Henry in this case. Okay, multiply them. Okay, differentiate them and multiply them. Give you here. VL equal to 37.5 e power minus 0.5 t ut. Okay, now in this case, the questions ask you for more. It's ask you for I6 ohm. Okay, for I6 ohm, you can see that try to derive them in the term of IL, in the term of IL. Okay, for time less than 0, okay, for time less than 0, okay, the inductors is, okay, you can see that this branch is already short circuit, right? The inductor is, okay, the inductance value equal to 0, okay, due to this short circuit, okay, therefore it have no current flow at the 6 ohm. Therefore, I6 ohm equal to 0 during the time. But for time greater than 0, you know VL, okay? VL equal to L di dt, okay? You take derivative of this, okay? Take derivative of IL, substitute them, you get here. And you know V, you can find I. The voltage VL, I6 ohm equal to VL divided by 6 ohm, okay? Okay? Substitute them, give you here. And in this form, you can see that in this form, okay, I6 ohm will be equal to 6.25 e power minus 0.5 t. Okay, it means sooner or later is, okay, for the time infinity, I6 ohm will be 0 again due to when the inductor is full charge at time infinity, the inductor perform like short circuit. If it's short circuit, all current will be flow in the inductor part. Okay, now in the overall point of view, we will summarize this procedure. Okay, IL for time less than 0 equal to 25 amp. Okay, IL at time infinity, when time greater than 0, you turn on another one source. Okay, therefore the source will be double. Therefore the current will be increased double from 25 to 50 amp. IL for time greater than 0, it will be increasing from 25 to 50 by the chair. 50 minus 25 e power minus 0.5 t. Okay, you can see, you can compute as the initial value, the constant by, okay, you set the 1.3 equal to 1.1. Okay, and next step, VL for time less than 0, due to VL equal to L di by dt. If IL is constant, VL equal to 0. Okay, VL equal to 0. And for time greater than 0, okay, take derivative of this term 50, take derivative of L di dt, take derivative of 50 minus 25 e minus 0.5 t. You get here. Okay, VL at time equal to greater than 0, it equal to 37.5 e power minus 0.5 t and decreasing to 0. Okay, and for I6 ohm, okay, the current flow in the 6 ohm part, okay, for time less than 0, it equal to 0. Okay, and time greater than 0, it jump to 6.25 amp and gradually drop to 0 soon. Okay, you can see that in this case, from this question, you compute IL, VL, and the I6 ohm. Okay, only IL that show you it gradually change when the switch is activated. Okay, it gradually change from 25 amp to be increased a little bit, reach to 50 amp. Okay, but the other such as VL and I6 ohm can change suddenly, jump from 0 to 37.5 volt and will be gradually drop after that, or jump from 0 amp to 6.25 amp, okay, and gradually drop after that. Okay, now we go to the last part. Okay, for the last part is the driven RC circuit. The driven RC circuit is okay. The driven RC circuit is the circuit that contains the resistor and the capacitor. Okay, but in this case, it's different from the previous. Okay, in the RC, the sort free. The sort free is mean the circuit that contains the resistor and the capacitor. Okay, and you remove the sort. The current and the voltage will be dropped to zero. So, okay. But in this case, the driven RC circuit is mean for time less than zero, it may be have some sort, or maybe don't have any sort in them. Okay. But for time greater than zero, you may be add some sort or remove partial of the sort. Okay, the current and the voltage will be drop or increasing or decreasing to some certain value in another next step. Okay. Now for the driven RC circuit, we will use the same technique as the previous technique that I gave it to you. The driven RC circuit, you must determine VC or the inductors, capacitor voltage first. Okay, the capacitor voltage that you must determine is separate in 4 steps. Okay, the first one, determine the capacitor voltage at time less than 0. At this point, the capacitor, well, the capacitor structure will be performed like open circuit, and you can use the DC analysis method to determine the capacitor voltage. Okay, next one, determine the capacitor voltage at time equal to infinity. Okay, at time equal to infinity, you can use, okay, see the capacitance as the open circuit. Okay, and use the DC analysis method to determine the capacitor voltage. Okay, next one determines, okay, capacitance voltage for time greater than 0 by determining the equivalent resistor and the equivalent capacitor by Q all independent source, or it means all independent source must zero out. Okay, and after you get the equivalent resistor and the equivalent capacitor, you can determine the time constant by multiply between R and C that you get from that step. Okay, and the total response we see for time greater than 0 equal to we see at time infinity that you determine from the 1.2 step. Okay, minus with I times at multiply with E minus T divided by tau or the time constant. Okay, and next one, the last one, you can determine the constant we tie at this step by set the 1.1 equal to 1.3, or set time VC at time less than 0 equal to the VC at time greater than 0. If you would like to determine the other parameters such as IR, IC, VR, or the other parameter, you derive them from VC only. Okay, for RL circuit, you must determine IL. For RC circuits, you determine VC. Okay, VC. Now, in order to give you more understand, we will provide you some example case. Okay, from this circuit is considerably difficult. Okay, it's considerably big. Okay, the circuit will be pressed in the top position for a long time. Determine and sketch the capacitor voltage or the VC, and determine and sketch the capacitor current IC. And after that, the questions ask you to determine and sketch the resistor current that show in the diagram. Okay. Now, in this case, the circuit checking for time infinity. If the time infinity, the switch is already pressed in the bottom position for a long time, and the bottom position have the 50 volt drive to your circuit. Therefore, the voltage VC is not 0. Okay, it have some sort drive in your circuit. It means it's the driving source. If it's the driving source case, okay, you must compute 4 steps of the VC. Okay, 4 steps of the VC. We start by the first one. We determine VC at time less than 0 first. VC at time less than 0, okay, press in this position. You can see that the bottom circuit is, okay, in order to make you more clearly, okay, we will redraw them, okay, redraw them. This circuit structure, this is size 60, 250 volt will be flow in this circuit itself. It's not effects to the VC structure. Therefore, you can eliminate this circuit part, okay, and in this case, we assume any transient in the circuit diode long ago, removing the pure DC circuit, and the capacitor act like the open circuit to the DC source, okay, and this circuit will be eliminated, okay, you can erase them, okay. Now, from this circuit structure, you can see that the circuit contains only 3 elements, 1 voltage source, dry 2 resistors, and the VC is the voltage across 50 ohm, and the 50 ohm is already series with the 10 ohm. Okay, therefore, VC you can compute from the 3 elements of them very easy by apply the voltage dividers technique. Okay, VC equal to the total voltage that you supply 120 multiply with the voltage, okay, that the VC take. Okay, VC is take at 50 ohm and divide by the sum of them. Okay, therefore in this case you can see that the VC equal to 100 volt. Okay, the next one, the second part is at the time infinity. Okay, at the time infinity, what happened? The circuit structure changed the structure type because, okay, the switch is pressed in the bottom position. And what happened? You can see that if it pressed in this position, you can see that in the left hand structure, okay, 10 ohm and the 120 volt will be the branch is broken. If the branch is broken, you can discuss them. Okay, discuss them. And 2 of them will be connect in this structure, you can redraw them. Okay, redraw them. Now, after you redraw them in the more systematic, okay, you can see that resistor and this resistor, 250 resistor will be connected in the parallel. Therefore, you can combine them, okay? And the capacitor is performed like open circuit. We assume any transient in the circuit diode long ago, removing a pure DC circuit, okay? The capacitor act like the open circuit to the DC current, okay, here. And 2 of them will be connected in the parallel, okay? 250 parallel will be give you 40 ohm. Now in this case, VC will be the voltage across 40 ohm, okay? And it have only 3 elements left, okay? 1 voltage source, 2 resistors will be connected in the series structure. You can determine VC or V 40 ohms by using the voltage dividers technique, okay? VC equal to the total voltage that you feed to them, 50, okay? Multiply with the resistance, okay? It takes. The VC will be a voltage across 40 ohm, okay, and divide by the sum of them, okay. In this case, you get VC at time infinity equal to 20 volt, okay. VC for time less than 0 is equal to 100. Now, you determine VC at time greater than 0. You get, okay, in order to determine R equivalent and C equivalent, if you don't see them clearly, you must redraw the circuit for time greater than 0. Okay, for time greater than 0, when you redraw the circuit, you can see that you cannot see them clearly because it has some voltage or some current source in here. You must kill every source that you have. How to kill the voltage source? You kill by short circuit them. Yes. When you kill them by short circuit, okay, you can see that, okay, 60 will be parallel with the 200 and parallel with 50. Very easy. Okay. Therefore, 3 resistors will be connected in the parallel structure. You can simplify them to provide you only a single resistor or the equivalent resistor to substitute them in the time constant. Okay. Therefore, equivalent resistor equal to 24 and the equivalent capacitor will be equal to 50 millihenry. Okay. You get the time constant in here. And after that, you substitute time constant and the capacitance voltage at time infinity into the general solution form of the RC circuit. Okay, RC circuit, VC at time infinity equal to 20. Okay, and time constant equal to 1.2. Okay, substitute them, give you here. After you get V in the overall solution in here, you determine the fourth step. The fourth step used to determine the initial condition by taking advantage from the third characteristic of the capacitor. It is impossible to change the voltage across the capacitor VC by among a finite amount in 0 time. Okay, VC for time less than 0 is equal to 100. VC for time greater than 0 is equal to 20 minus V e power minus 0.83 t. Okay, you substitute every t to be 0. Okay, 0 multiply anything give you 0. Anything power 0 give you 1. Therefore, 100, okay, equal to 20 minus V. Okay, therefore V will be equal to minus 20 minus 80 instead. Okay, now in this case, you substitute them back, it gives you a solution. We will provide you VC equal to 20 plus 80 E minus 0.8 t. Okay, and here, next one. Okay, if the questions would like to find the other parameter, derive them from VC. Derive them from VC. Okay, for the VC, okay, for the VC IC that you compute from VC, IC equal to C dV by dt. But for time less than 0, VC is constant. Okay, is equal to 100 volt. Take derivative of the constant. Take derivative of 100 give you 0. Therefore, IC for time less than 0 is equal to 0 too. Okay. Now for time greater than 0, okay, VC is no longer constant. It equal to 20 plus 80 e power minus 0.8 t. Okay. Take derivative with respect to time. Okay. The first term, the take derivative of 20 give you 0. Okay. Take derivative of EAT give you A EAT. Okay. Give you A EAT. Okay. After that, you can reorganize the equation, get the IC equal to minus 3.3 e power minus 0.5 t. Sorry, not 0.5. Oh, sorry. Yeah. Okay. E power minus 0.8 t. Okay, 0.83. Okay. Next one. The questions ask you for the current flow in the 200 ohm. In this case, for time less than 0, you must determine each time. Okay. You determine you determine the current in the form of VC if it's possible. But for time less than 0, the switch is placed in the top position. Therefore, the current that flow in here is not affected from the outside. Okay, I depend on 50 volt and 60 ohm and 200 ohm. Therefore, the current flow in this part will be not affected from the other. Therefore, from the Ohm's law, I equal to V divided by R. 50 divided by 60 plus 200, or 50 divided by 260 give you 0.19 amp. Okay. Now, you compute another times value. Okay. For time greater than 0, the switch is already placed at that position. Okay. Therefore, the value of them is here. Now, in this case, you kill. Okay. In this step, you must kill this sort first. Okay. I for time. Okay. I for this time value is equal to, you can see that I equal to VC. Okay. You can see that in this circuit structure, 60 parallel with the 200 parallel with the 50, right? Therefore, you know the VC across that all three. Therefore, you can eliminate two that you are interesting, okay? I equal to V divided by R, okay? You know VC, you can find I throw in the 200 ohm easily, equal to I equal to VC divided by 200, okay? You get here and here, okay? Reorganize them. I equal to 0.1 plus 0.4 e power minus 0.83. Okay. Now in the overall point of view, what happened? Okay. In the overall point of view, okay, the voltage will be the VC, the capacitance voltage equal to 100. Okay, fixed in this position. And for time infinity, it will be dropped to 20 in here. When the switch is pressed position, okay, it drive by another source that's smaller, okay. Therefore, we see for time greater than 0, okay, it will be gradually drop, okay, and reach to 20 soon, okay. For time less than 0 equal to 100, time greater than 0, it equal to 20 minus V e power minus 0.8 t, okay. It equal together at time equal to 0. You can conclude, okay. We had, okay, the initial condition, the constant that you would like to find equal to 80, okay. And for IC, for time greater less than 0, you can compute them from the circuit structure itself or compute from the VC, okay. For time less than 0, the VC is constant, IC equal to its derivative of VC. If it's constant, its derivative equal to 0 too, okay. And for time greater than 0, it will be, okay, jump to be minus 0.33 amp and gradually drop to 0 soon, okay. And the current flow in the resistor branch will be here. For time less than 0, okay, the current will be driven by the internal source, okay. Okay, it equal to 0.19 amp, okay. And for time greater than 0, it driven by the capacitance value, okay, is equal to V divided by R, okay. It jump to be 0.5, okay, amp and will be gradually drop to be 0.1 amp soon, okay. Now, in order to give you more understand, okay, I will provide you another one example in here. Okay. For the circuit of the following figures, determine and the sketch the inductor current, determine and the sketch the inductor voltage, and determines IL and the VL at time equal to 8 milliseconds. Okay. Yeah. The circuit is very simple. Okay. Because, okay, it have okay. Okay. For time less than 0, the switch is, okay, the source is not activated yet, okay. The source is not activated yet, it means it have no source in here, okay. If it have no source, nothing here, okay, IL equal to 0 too, okay. As any transient in the circuit die out long ago, removing the PL, okay. Therefore, IL equal to 0 because it have nothing left. IL at time infinity, the inductor perform like short circuit. And the source is already equal to 20 volts for a long time. We assume any transient in that circuit died out long ago, leaving a purely DC circuit, and the inductor act like the short circuit to the DC current. Yeah, it equal to 20. Okay, if it's short circuit in here, I equal to V divided by R. Okay, equal to 20 divided by, sorry. Yes. Sorry for that. No, for that. Sorry. Okay. Okay, it equal to 20, okay, divided by 200 ohm. It equal to 0.1 or 100 milliamp. Okay. And next step, determine IL for time greater than 0. Determine IL for time greater than 0. You know about the equivalent inductance equal to 4 and the equivalent resistance equal to 200, okay. You know the time constant equal to 0.02, okay, second. And the general solution of the IL circuit in this case, you can write them in the term of the IL at time infinity and time constant. IL at time infinity equal to 100 milliamp, okay, and the time constant equal to 0.02, okay. You substitute them in the general solution form of the RL you get here. You have only one problem that about this constant, about this unknown constant, I prom. And you can compute I prom during you text the, okay, IL for time less than 0 and the IL for time greater than 0 by taking advantage from the third characteristic of the inductor. It is impossible to change the currents through an inductor IL by a finite amount in 0 time. Therefore, in this case, IL for time less than 0 is equal to 0. IL for time greater than 0 is equal to 100 minus I e power minus 50t. You substitute every t to be 0 in here. 0 multiplied minus 50 give you 0. Anything power 0 give you 1. Okay. Therefore, you know that, okay, you get I times equal to 100. You substitute them back, give you here. Yeah. This is the IL for the general solution form. Okay. And if you would like to find IL at time equal to x millisecond, you compute them, okay, substitute x millisecond in the ILs, okay, the general form of the IL, and you get 33 milliamp. Okay. Now, if the questions would like to ask you for more, it's ask you for VL and can derive them from IL. Derive them from IL. VL for time less than 0, IL is 0, is constant. VL equal to the derivative of IL respect to time. If IL is constant, VL is constant to 0 too. Okay. And VL for time greater than 0, VL for time greater than 0, VL equal to IL equal to 100 minus 100 e power minus 50 t. Okay. And take the derivative of the first one. Take the derivative of the 100 give you 0. Take the derivative of E AT give you A EAT. Okay. Substitute them, reorganize them. You get VL at the times greater than 0 equal to 20 E minus 50 t. And at time equal to 8 milliseconds, okay, VL will be equal to 30.4 volt. Yeah. In the overall point of view, IL for time less than 0 is equal to 0 because the source is not activated yet. At time equal to infinity, the source is activated for a long time, and it makes the IL at time infinity equal to 100 milliamp. Okay. IL for times greater than 0, it will be increasing in the exponential form and reach to that point soon. Okay. You can find the unknown constant by substitute, okay, 1.1, set 1.1 equal to 1.3. Okay. You get, okay, the constant equal to minus 100 in here. Now, next step, you determine VL from the IL later. Okay. For time less than 0, IL is constant. Take derivative constant give you 0. Okay. For time greater than 0, okay, take derivative of this term will give you 20 E minus 50 T is here. Okay. And when you observe them again, you can see that IL graduation always. Okay. But the other parameter can be graduation or sudden change. We don't care. Okay. Now, another one example that we show you is here. Okay, for the circuit of the following figures, okay, is determine and the sketch the inductor current, determine and the sketch the inductor voltage, determine and the sketch the resistor current, and determines the resistor current at time equal to 1.5 milliamp. Okay, for this circuit structure, you can separate the circuit into time zone for time less than 0 and time greater than 0. Okay, checking again for time less than 0. The switch, okay, the switch used to press in this position for a long time. It means it have the current will be flow in this short circuit part. When the time equal to 0, the branch is open, 10 milliamp source will be drive to your circuit immediately. Okay. Now for time less than 0, okay, for time less than 0, the circuit part will be short circuit in here. Therefore, it have no current flow is all current will be flow in the short circuit part. No current flow in another 3 element left. Okay. Therefore, IL equal to 0 at that time. From the switch branch is closed or the short circuit. No current flow through the 10 milliamp inductor. Okay. And for determine IL for the times equal to infinity. Equal to the infinity is mean the switch is already open for a long time and the inductor perform like short circuit. Okay, short circuit. You can determine IL. We assume any transient in the circuit died out long ago, leaving the purely DC circuit, and the inductors act like the short circuit to the DC current. You can determine IL from the current dividers technique. Okay, IL equal to all current flow equal to 10 milliamp. Okay, and multiply with the resistance in another branch. Okay, the resistance in another branch is the 60 ohm and divide by the sum of them. Okay, 60 plus 40 will be give you 6 milliamp. Okay, now the next one determines IL for the time greater than 0. In this step, you must use, okay, you must compute the equivalent inductance and the equivalent resistance. Now, you check the circuit first again, okay? You can see that for time greater than 0, for time greater than 0, the circuit structure in this form, right? In this form. And the current source, how to kill the current source? You must kill by open circuit them, right? If the one is open circuit, okay, this 60 ohm and the 40 ohm will be connected in the series together and the series with the inductors later. Okay, therefore the time constant, the equivalent resistor equal to 100. The general solution of the RL is IL equal to IL infinities minus I hat e power minus t divided by tau. You know I infinity, you know the time constant. You substitute them, give you here. Okay, and you still have some unknown in here, and this unknown you can determine from, okay, you set the solution in the 1.1 equal to the 1.3 at that step. Okay, find the unknown constant. Okay, the third characteristic of the inductor, it is impossible to change the current through an inductor IL by a finite amount in 0 time. IL at time 1.1, IL at time less than 0, IL at the time greater than 0. Both of them is equal when you substitute everything to be 0. E power minus 0 give you 1. Okay, therefore we will provide you in here. Therefore you get the constant I had equal to 6 milliamp. Okay, IL, the general form of the IL equal to 6 minus 6 e power minus 1000 t ut. Okay. Now, if the questions ask you for more, ask you for VL at time less than 0 or greater than 0, derive them from IL. Derive them from IL. For time less than 0, IL equal to 0 and constant during the time. Therefore, VL equal to 0.2. Okay. But for time greater than 0, VL equal to L di dt. Okay. You know IL equal to 6 minus 6 e power minus 1000 t. Take derivative of the first constant 6, okay, give you 0. Okay. Take derivative of another one, okay, you get 1, okay, you get 0.5, okay, in here. After that, you substitute the multiplication technique, provide you here. Okay. Now, the questions ask you for more about IR, the current flow in the 60 ohms resistor. For time less than 0, okay, for time less than 0, the switch is drive by here, okay, it have drive by 2, okay, 60 ohm, okay. And for time greater than 0, it equal to here. Okay, it equal to, okay, drive by this and this, okay. Okay, I6 ohm at time equal to 1.5 millisecond equal to 4 plus 6 in here. Substitute them, give you 5.34. Okay. Okay, now in the overall point of view, IL for time greater than 0 is equal to 0. IL for time greater than 0, it will be reached to infinity equal to reach to 6 milliamps soon, okay, and increasing in the exponential form, okay. And okay, VL for time greater than 0, due to IL is constant, okay, VL equal to LDI by dt will be 0.2 during that time, okay. And for time greater than 0, take derivative of the exponential form give you here will be jump and decaying exponential form jump to be 0.61, okay, and reduce to be 0 soon, okay. And IR for time greater than 0 is equal to here, okay, 0, and for time greater than 0 is equal to, okay, jump to be 10 milliamp and drop to be 4 milliamp soon. Okay, I think I will provide you so many examples. Okay, you will give you more understand about that. Okay, but remember that the most important thing in the circuit structure, even though you listen 1,000, you see the slide. I don't know how many hours you spend to see the slide. Okay, but if you never do them by yourself, you never really understand that. Okay, and you cannot do them until you start to do the exercise by yourself. Okay. Any question?
No question.
Okay. I think it's already, the time is almost close. Okay. Now we already finished the RL and the RC circuit. The next time we go to RLC circuit in the chapter 9. Okay.
Okay.
Okay. Now dismiss. Okay. See you next time.
See you, John.
Thank you, John.
You're welcome.